This video will cover the hydroboration of alkynes. Just like other additions to alkynes, the mechanism of this process will resemble the hydroboration of alkenes. Remember, in the first step of hydroboration of an alkene, the addition of borane occurs. Remember that the structure of borane looks like this. The boron center is electron deficient, making a good target for the nucleophilic alkene. The alkene adds to the borane in such a way as to create the less substituted borane intermediate. In the final step, peroxide and sodium hydroxide oxidize off the borane to give the alcohol. This results in anti-Markovnikov addition of water. In alkynes, the process is very similar. In the first step, a borane is added to the alkyne. Because in the case of the alkyne, unlike the case of the alkene, we have two pi bonds, so we want to prevent the addition of two molecules of the borane. In order to do so, we use a type of borane called dicyamylborane. The bulky cyamyl groups prevent more than one equivalent of the borane from adding to the alkyne. Just like in the case of the alkene, we see the dicyamylborane add to the alkyne in such a way as to give the less substituted borane. Oxidative removal of the borane with peroxide and sodium hydroxide produce an enol intermediate. This is similar to what we saw with the mercuric ion catalyzed hydration. And just like with the mercuric ion catalyzed hydration, we see rearrangement or tautomerism from the enol to the keto form. In the case of hydroboration, however, this is base catalyzed. The overall process of hydroboration of alkynes gives us the anti-Markovnikov product. Again, to better understand why we get the anti-Markovnikov addition, we need to look at the mechanisms. Hydroboration of an alkyne occurs in exactly the same way that it occurs to an alkene. The alkyne attacks the boron, creating a partial negative charge on boron, which allows the hydride to attack right back. This forms a similar transition state as the hydroboration of the alkene. Remember that the reason for the regiochemistry that we observed in the hydroboration of alkenes is that the negative partial charge forms on the boron, and the largest partial positive charge forms on the carbon opposite the boron. The larger partial positive charge is more comfortable on the more substituted carbon, which is why the boron adds to the less substituted carbon of the alkyne. Once the alkyl borane is formed, peroxide and sodium hydroxide are used to oxidize off the boron, making the enol. Once formed, the enol rapidly tautomerizes to the keto form. This occurs through a base-catalyzed mechanism. In the first step, the base deprotonates the enol. This enolate has resonance. Protonation of the other resonance contributor gives us our final keto product. This is how we end up with the anti-Markovnikov addition through hydroboration of alkynes.